Here we go, recording this lesson for the purpose of each and everyone that is busy studying mathematics at this point in time, and good luck to them. So our homework calculations, some of them were pretty easy, but it's just the way that they ask the question. So we're looking at number one, and it says an object of mass 7 kilograms initially at rest is acted on by a force of 14 Newton for 10 seconds. So this is the situation that I've drawn. There's my little object. My object is always something like a tennis ball or something, but 7 kilograms, a medicine ball in this case, right? There's a force of 14 Newton working on it for a period of 10 seconds. Initial velocity is 0. Now they ask us to calculate the gain in momentum. So gain in momentum, we can bring back to the change in momentum. Because it has an initial velocity of 0, its initial momentum is 0. So any change in momentum is going to be a gain in momentum. Well, we know that this m delta v is the change in momentum. But we also know the following. We know that the resultant force times time impulse is also equal to the change in momentum. And because we have a force that is causing this change in momentum for that specific time period, this is what we will be using to calculate the gain in momentum. So substituting my values, 14 seconds is 10. So the change in momentum, and I'm just going to do it in the proper way, is 140 Newton seconds. So that is the change in momentum. Remember, change in momentum is equal to the impulse. After this, they ask, well, calculate the velocity, the final velocity of the ball. And now I'm going to go back to this equation because I know that my change in momentum, although it's equal to the impulse, it is also mass and change in velocity. So I can state it like this. I can state change in momentum is mass, and it's my final minus initial velocity. Luckily, well, not luckily, but yes, my initial is 0, so it simplifies my whole calculation. My change or gain in momentum was the 140. My mass is the 7 kilograms. I want final, and my initial was 0. I know this is ridiculous, but it's worth it writing in because then it's not just throwing away a symbol and a value. It's that little bit of, I know the initial velocity is 0. Tell your examiner exactly that. Okay, so if we just manipulate this quickly, this would be 7v equals 140. Therefore, v is 140 divided by 7. I'm going the long route. You could have gone directly and say v is equal to 140 divided by 7 gives me 20 meters per second. Right. Any question on this? Except that I'm...
Do they give us the formulas in the exam, or must we memorize these two?
Ooh, that is a very good question. Do you know what? I can quickly check for you. Let me check on the end of the lesson. Just quickly ask me again. There is some formula. I think they just give momentum. I think they just gave the formula of P equals mv. That's the only one that they give. The rest you must all recall. So, but let me just check at the end quickly. I'll draw up a question paper and we have a look at what is there. Right.
Okay, thank you, sir.
Perfect. Right, let's look at question number 3. question number 3, it's very similar in the way that it asks. And it says an object mass 5 kilograms is initially at rest. It's acted on by a force of 8 Newton for 12 seconds. And then brought to rest by a different force in 20 seconds. Let's see, what do they want from us? The first, for A, they say show that the change in momentum due to the 8 Newton is 96 Newton seconds. Okay, so they want us to prove the following, that change in momentum is equal to that. So again, we're going to use my principle that we just said. Well, change in momentum is equal to F res times delta T. And listen, this is the only force, that 8 Newton is the only force working in on it. So therefore, that is the resultant force. All right? Just make sure always this definition is for resultant force. So if there's more forces, you need to take those into account. But if we have 8 times the time 12 seconds, then we get the change in momentum as 96 Newton second, right? So that's easy enough. Calculate the speed of the object after 12 seconds. Okay, so let's do that. Again, we can do the same. It's initially at rest. We use change in momentum as mass final minus initial. Mass in this case is 5. Change in momentum is 96. I want final, and initial is 0. Having that, immediately we can say V is that 96 divided by 5. What is 96 divided by 5? Gives me 19.2. 19.2 meters per second. Right. Again, exactly the same as the previous question. Now, though, they say the force needed to stop the object in 20 seconds. So this is now what has happened. This object has picked up that speed due to the 8 Newton. The speed is the 19.2 meters per second. So it's moving at that, so it has the specific momentum. So in this case, that would be its initial momentum, and after 20 seconds, its momentum will become 0 because its velocity is becoming 0. So let's see, can we calculate this? And now we're going to do the expansion of this formula. What do I mean? I mean, F res delta T is my change in momentum. That means mv minus u. Right, let's substitute in that we have in here. We want that force that brings it to stop. The time that it takes is 20 seconds. Mass of the ball is the 5 kilograms. Well, it brings it to rest, the question states. So my final velocity is 0, and my initial is that I calculated is the 19.2. Let's calculate my resultant force. So it's going to be a negative because it's in the opposite direction of motion. 19.2, well, negative that, times 5 gives me the negative 96, because we had that momentum of 96. We could just have done that and divided by 20. So it gives me a negative 4.8 Newton. So that's the force needed to stop it. All right. The negative means it's in the opposite direction of motion. So depending on what your question paper looks like, 4.8 Newton direction to motion would be the most proper answer that you can give for that one. Right. Any questions for this?
No.
All right. Let's move on to the next question. Was question number 4. Question number 4, as I read it, I thought, wow, there's something weird in here. But let's tackle it together. I'm glad you guys are joining me. I'm glad I have 3 mathematicians with me that you can help me. So let's look at it. They say we have this stream of identical atoms of mass 1 times 10 to the power negative 25 kilogram hitting a vertical surface. And it's hitting it perpendicular with a speed of 750 meters per second at a rate of 2,000 atoms per second. The atoms stick to the surface on impact. Now they want us to calculate the loss of a single atom. Okay, so identical atoms, we have the mass and we've got the velocity, so we can calculate the change in momentum. That's actually what they want us to do, calculate change in momentum. We can do that. So we can say change in momentum equals mass final minus initial velocity. The mass is that 1 times 10 to the power negative 25. My final velocity is 0. My initial velocity is the 750 meters per second. So the value is going to be negative because it's a loss of momentum. And the wall is gaining that amount of momentum. Let's do the calculation. So 750 times 1 exponent negative 25. And we get to an answer of 7.5 times 10 to the power negative 23. And it is, well, we can use Newton's second. That is unit. There's nothing wrong if you said kilograms meter per second. That is the base unit for this. Right? Now, okay, so it is negative, but they refer to the loss of momentum. So if you said loss of momentum using P would be 7.5 times 10 to the power negative 23 Newtons second. So proper answer. Cool. Average force of the atoms on the surface. Now, this is a weird question for me. If we look at the average force, the only way we can get this if we say if res delta t equals the change in momentum. We know what the change in momentum is. The change of momentum is at 7.5 times 10 to the power negative 23. We want the resultant. But this is where my mind gets a bit stuck at this point in time. They tell you, you're looking for a time in there. They give us a rate of 2,000 atoms per second. So how do we use that? Can we use that for the time? Any suggestions from your side?
We can times the change in momentum by the 2,000, and then the rate would be 1 second because there's 2,000 atoms in 1 second.
Yeah, Jana, I think you're right. Because it boils down to this, isn't it? If we use it like that, because that's what you come out with. And that's the simplest that I could also work with that, and that times 2,000 then basically. if we do it like that.
Yes, I did it like that.
Did you do it like that?
Yes.
Okay, fantastic. So if we times the 7.5 times 10 to a negative 23 times 2000, we get to 1.5 times 10 to a negative 90. Listen, this is the weirdest way that I've seen it asked in my 14 years of teaching momentum. So it's really a weird way of doing it, but it's interesting that they bring this into relation with this. Listen, our last topic that we do is nuclear physics, where we deal with atoms. Now, I've seen them bring it into relation with atoms colliding, and that's where the 2D gets into. But this is also an interesting way that we can consider that, giving you a rate. Okay, right, that was question number 4. Now we have question number 9, and question number 9 is a nice question. I like question number 9 because it brings the whole thing together. Here's my drawing of this. Very nice. They give us a graph as well. They start off by saying, listen, we have this ball B, 1.2 kilogram. It has a velocity. You need to refer to the graph to get the velocity. They say from the graph that is positive 4. So immediately they also hint and say, listen, there's a specific direction that you need to consider, and the initial direction of ball B is positive. Then it hits a stationary ball S with a mass of 3.6 kilograms. Right? So this always indicates my little collision. After the collision, well, if we go to our values, we can see that ball B is now moving in the opposite direction because it's got a negative velocity. Velocity reading down from the graph is a 0.8 meters per second. We don't know anything about ball S, whether it's moving and which direction, we don't know. The other thing that we do get from the graph is we can get the time that the two objects, B and S, are in contact with each other. That's that diagonal line indicating the time that they are in contact with each other, the time that it changes from one velocity to the other, from one momentum to the other, the time for the change in momentum. And we can read that down as 0.08 seconds from it. And I think if we just refer to the values, I took it down, was the final was the 0.26 minus the 0.18 seconds. That comes from your graph. Okay, so that's all the information that they give us at this point in time. Let's look at the questions. First question that they ask, they say, state the significance of the positive and negative values for V in this figure. Well, we know velocity is a vector. Therefore, positive and negative gives direction. It indicates direction. That indicates direction. B. Use the figure to determine for ball B during the collision with S, the change in momentum of ball B in Newton seconds. Let's go for it. And it's for ball B. So change in momentum, mass, final minus initial velocity. Right. What is the mass of ball B? It's the 1.2 kilogram. My final velocity is 0.8, but it's in the opposite direction to the one that I chose, positive. So final is the negative 0.8, minus initial, which was positive 4. So my change in momentum that I calculate is then 0.8 plus 4, that is negative 4.8 times 1.2, and I get negative 5.76 Newton seconds. I'm going to leave that like that because they only ask me to calculate the change in momentum, right? Depending on your question, you will need to interpret that negative as a direction. So negative means in the opposite direction to motion. That is my direction that you need to add. So this was BI. Let's look at BII. What do they want? The magnitude of the force acting on the ball. See, this is again the nice thing that they do here. They know there's negatives and positives in there. Therefore, they only refer to the magnitude thereof, right? How do we get the magnitude? Well, we know change in momentum is equal to my impulse. Impulse, F rest, delta T. We calculated my change in momentum now. And we have, and I'm going to use the real value. Always use the real value. The negative 5.67. Doesn't hurt anyone. Remember, your final answer is just going to be a magnitude, so you're going to leave out the direction. I want the force. The time we said was the 0.08 that we calculated. So you can either do this little calculation and showing the two values in there saying, listen, I know that for that time, it's the final 0.8, and that gives me my 0.08 in there. So therefore, my resultant force, yes, it's going to be negative, but my final answer I will state it as positive. Divide by 0.8, and I get 72 Newton. Right? So therefore, my resultant force in this whole collision is 72 Newton magnitude. So what does this mean? It literally means this ball has applied a force of 72 Newton on that ball to change its direction. But it's also true for ball B because this Newton's third law applied a force of 72 Newton on ball S. So I would expect in the next question to calculate to get my velocity of ball S positive in that direction. That's what I would expect. Let's go see if it's true. This is now question C. Calculate the speed of ball S after the collision. Now, there's various ways that you can do it. I'm going to do it with the conservation of momentum. I am going to say the following. I will start and say the sum of momentum before is equal to the total sum of momentum after. I have my ball B in the beginning with a mass and a velocity, and I can see B, well, U for initial, plus mass of S, U of S. This is easy, that one is 0. This one is the 1.2 times my 4, and I have my initial. After, I again have mass of B, V of B, plus mass of S, V of S. Mass of B is the 1.2. Velocity is in the opposite direction, negative 0.8. Plus, now my unknown 3.6 Vs. That's the one that I want to calculate. All right, let's do the calculation and see where we get to. So 1.2 times 4 is 4.8. I'm going to have a negative value over here. So let's just write it in 4.8. 0 I'm going to leave. I'm going to bring this directly over and say plus that, which is the 1.2 times 0.8 is 0.96, right? And this is all 3.6 Vs. Add the two, divide by 3.6. I'm writing it in for all intents and purposes. So Vs is then 0.96 plus 4.8 gives me the 5.76. At least I could do the same. Look at that. It's equal to the change in momentum, which it should be. Okay, it should be equal to the change in momentum. Divided by 3.6, and I get a positive value of 1.6 meters per second. So if they want direction, 1.6 meters in the direction of initial motion of B. That's what it will be. So it's a positive value in there. So this was a long way to do it. Obviously, you can skip a few steps in there. The principle is important. The principle is important.
So in the previous question,
Yes.
how did you get to 72?
So the step there, and hopefully it would be that value divided by the 0.08.
I got 12.
Hey?
I got 12 minus 12.
Did you get 12? Oh, dear me. Thank you. Check me. 5.76 divided by 0.08. Why do I get 72? What's wrong with my calculator? Ooh, did I do 0.8 or 0.08? 5.7. Still get 72. So just...
Oh, I see what I did wrong. Sorry, I calculated wrong.
No worries. It is good. You should check me always. Listen, this is the nice thing, and that's why even if I do a recording, it's good that there's one or two students available so that they can help me and check. It is more realistic that way. Right. So, and this is why I prefer doing it the long way, showing the values and what you do in there as well, right? Then you can easily pick up a mistake that you made yourself. Okay, all happy up until this point?
Yeah, it's fine.
Right here. Okay, so guys, now we get to the last bit where they ask, use your answer in C and information from that figure 9.2 to deduce quantitatively whether the collision is elastic or inelastic. What does an elastic and inelastic collision refer to?
Elastic means that the kinetic energy before is equal to the kinetic energy after the collision.
Oh, fantastic. So this is it. Let's just get to the correct spot. EK before is equal to EK after. If that is true, then we can say the collision was elastic. If this is not true, if my EK before is not equal to my EK after, then it's inelastic. It means energy was lost.
What are the sources of energy loss?
Sorry, say again.
What are the forms of the energy transferred? Is it heat, air resistance, or like if two balls collide?
What? Usually most all our collisions, 99 that we have obviously in real life, realistically, is inelastic because the energy is transferred to sound. It's transferred to heat, as you said, now due to air resistance or friction. So all of that has to do with most collisions being inelastic. So we'll deal with elastic collisions just to show the principle in there as well. So let's do this quickly again. So we bring back from our whole thing. So we start with, and because we don't know, we need to do it as separate calculations. We need to go and calculate EK before, and that is a half MB UB, right? Because S doesn't have any kinetic energy, it's stationary. So let's do the kinetic energy of B. Ooh, kinetic squared, almost forgot that one. So what is B? It's a 1.2 kilogram, and it's got a velocity of 4 squared. So let's do 4 squared is 16 times 1.2 times 0.5 gives me a 9.6 joules. So that's my kinetic energy before collision. Let's see, after my collision, what do I have? So EK after, now we have both. Remember, energy is a scalar, it doesn't matter the direction. VB plus a half MSVS in there. So a half 1.2 and it is 0.8 squared a half 3.6, and what is the velocity of this that we calculated? 1.6 squared. All right, so let's do our calculation for that. It is 0.8 squared times 1.2 times 0.5. It gives me a 0.384 plus, let's do the other one, 1.6 shift square times 3.6 times 0.5. This gives me a 4.61. So if I do that, what do I get to? Well, not very much, 4.99994 joule. So I can say in this case the following: my EK before is not equal to my EK after. Do you see why we couldn't have started, for instance, with the principle and say this is equal to that and do the calculation? We needed to do it as separate calculations and then end with this. It's not, therefore collision is inelastic. All right, any questions on this?
It's all good.
So, guys, there's a second way that we can look at elastic and inelastic collisions, and that is by looking at the relative velocity or relative speed of approach to relative speed of separation. I will do an example on that on Friday, but for now, this is in essence what this whole chapter entails. I'm going to post 2 worksheets on Moodle, and I know there's some difficulty. Not everyone can get onto Moodle at this point in time, so I'll also do that on the WhatsApp group, right? And that will not be for Friday. It will only be for next week. So any questions and all of that that you have, you can obviously start looking at the worksheets, but any questions on this, together with the elastic and inelastic collisions and 2D motion, we'll discuss on Friday again, those who have questions. If there's no questions, well, then there's no point in having a class, but let's see what happens. All right, all happy?
Yes, thank you.
Okay, great. Thanks, guys. Do enjoy the rest of your Wednesday. Keep well.